Okay, hello everyone. My topic is non-destructive evaluation of properties of microperforated acoustic materials, and my goal is the same: to estimate non-destructively the properties of microperforated acoustic materials. And this is an outline of what I'll be presenting today. I'll start with an introduction, then an electroacoustic analogy, which is very important in the derivation of the equation, which I'm going to present today, and my approach and the governing equation, and the different hole profiles I've analyzed, then forward programming and inverse programming. So, what is a microperforated panel? So, microperforated panels are acoustic observers that are reclaimable, non-combustible, and environment friendly. So, before microperforated panel, the main sound absorbing uh, substance was porous materials, which had many problems. So, uh, this was a very suitable substitute for that, and it is mainly manufactured from plastics or metal. And as you can see in the figure, these are small pores or perforations, in other words, and it's a microperforated panel. Each of these holes or pores are sub-millimeters in size. Sub-millimeters means less than 1 millimeter. And due to these small pores, the acoustic resistance provided by the material is high, which enhances sound attenuation and is used for a wide range of sound absorption. And generally, a microperforated panel is 0.5 to 2 mm thick, and the holes typically contain 0.5 to 2% of the plate, and the hole diameter, as I have said, is in this range, which is a sub-millimeter range. Now, what are the uses of microperforated panels? Mainly, there are many uses. As you can see, it's used in a reception area, and it's also used in the engine compartment. This is the engine. This is the microperforated panel to avoid the noise of the engine. And these are all the other various uses where it's used for sound absorption: air duct silence, automatic mufflers, and highway noise barriers, etc. Now, what is my problem definition? So my problem, forward problem and inverse problem. Forward problem means to find the absorption coefficient of the microperforated panel from the incident wave using the properties of the panel. Now, inverse is basically the inverse to using the acoustic properties, using the absorption coefficient data, we'll be finding the acoustic properties and the incident wave characteristics. Now, I have started the electroacoustic analogy, and this is a very important analogy which we'll be using throughout, and it's basically used to reduce our acoustic system into an electric system which contains the voltage, current, resistance type. And in this analogy, our sound pressure is analogous to voltage in electricity, and volume velocity is analogous to current. Now, what volume velocity is basically is the rate of flow of medium perpendicular through a specified area S. Or in other words, it's basically area into U. U is the particle velocity, area into particular velocity. That is the volume velocity, which is analogous to current. And these are some of the elements, acoustic elements, which is acoustic mass, which is represented by a tube filled with the gas, as you can see. And this is the its corresponding electrical analogy, which we will be drawing this sign. And the steady state equation is given here: P is equal to I omega ma capital AU. P is the pressure, capital U is the volume velocity, as you know, and is the imaginary number -1, root of -1. Omega is the angular frequency, and the tilde sign represents that is an e power I omega t term, which is a time dependent term. That's it. Another element is acoustic compliance, which is represented by a volume of air, as you can see. And the electric analogy symbol is that of a capacitor. This is the steady state equation. Another material is acoustic resistance, which is represented by a mesh screen. And it's analogous to electricity is that of a resistor. And this is the equation for that. And there are acoustic generators: constant volume velocity type and constant pressure type. If you remember correctly, it's basically constant current EMF and constant voltage type of generator, which we have studied, I think, in the 12th standard. Now, this is an example that I used to familiarize with the concept of analogous electric current. Basically, there's a force is acting, constant force is acting. This T1, T2, T3 are the tubes, V1, V2 are the volume of empty volume, and RA1, RA2 are the resistance mesh. As it was given that the force acting is constant. If the force is constant and the area is constant, the pressure must be constant. That is why we use a constant pressure generator here. And now the volume velocity, that is basically the current flows through here. And first it goes through the T1, uh, which is the acoustic mass, which is the tube of gas, which is represented acoustic mass Ma1, and it goes through here. And when it reaches here, it has two options. Either it can flow to the V1 or it can continue to the next tube. V1, that is the we have just defined. It is acoustic compliance, and it's a tube which is M2, which are defined like this. Basically, similar to draw like this. Now, what is an impedance? Impedance is used in impedance is a main component which is used in the derivation of the equation that I'm going to show. So there are three terminologies. That is, first one is acoustic impedance, which is the ratio of pressure divided by the volume velocity through it. Next one is specific acoustic impedance. It is basically pressure divided by the particle velocity u. And there's another thing, characteristic impedance, which is equal to rho zero multiplied c zero, where rho zero is the air density, c zero is the speed of sound wave. And it actually comes as the ratio of effective sound pressure to the particle velocity of a free plane progressive sound wave. And when we do that, we end up with this term, and it actually depends upon rho and c, which is the characteristics of the medium. And it's called characteristic impedance. Also, it's called relative impedance. And throughout this presentation for ease, I'll be using this representation. Small z is specific acoustic impedance, capital Z is acoustic impedance, and capital Z with a subscript R is characteristic impedance. And what my approach? So this is my approach. This is called impedance approach, which I have used. So this is a typical microprofile panel, as you can see. B is the distance between the portions. D is the diameter portion. Capital D is the air cavity depth, which is there's a hollow space, or not a hollow space, hollow air cavity where nothing is there in between the microprofile panel and the rigid wall, which is denoted by capital T, and TH is the thickness of the MPP. And these are the assumptions to be used. That is, first thing is the distance between the pores is greater than diameter of the pores. If this assumption is valid, then we can consider each hole as an independent, not depending on the other hole. And if the distance between the pores is less than wavelength of the sound, then we can neglect this part that is in between the holes. That is, this metallic or plastic part we can neglect in our calculations. So if both of these assumptions are valid, then we can consider air inside the tube can be considered to be formed by a large number of thin coaxial cylindrical layers. It can be each is considered as an independent layer. Now this is the derivation. So consider this as this is one of the hole, and we just took a small cross section of it like this. This is a ring element, annular ring element, which inward radius r, inner radius r, and a thickness dr in this direction. And when we consider to look in this direction, x direction, and the thickness is dx, axial thickness. Dr is the radial thickness, r is inner radius. Now this is the free body diagram of the force acting. The force acting on inertia force driving this for this element. Inertia force, driving force, and these are frictional force on the inner side and the outer side. Now these are the equations. Why driving force is equation is because psi is the pressure gradient. So basically psi dx means the differential pressure across the element. Now we know pressure multiplied by the area gives the driving force. 2 pi r dr is basically this the area that you can see right here, 2 pi r into dr. So this is the driving force. Now these are the friction force, which is derived like shear stress acting into area. We know shear stress is mu du by dy, which is mu du by dr, and the area in which it is acting, that is the area which I think you cannot see, this area, which is nothing but 2 pi r into dx, the axial direction. This is the friction force, and we got the friction force in the outer direction using mathematics, using this equation. And inertia force is basically mass times acceleration, the resultant force which we get by using Newton's second law, which is mass times acceleration. We know 2 pi r dr dx, this whole term becomes volume into rho, means volume into density means mass. Now we need acceleration, which is du by dt. We know du by dt becomes I omega u, reduce the particle velocity. And if we put all these equations, we'll find a partial differential equation like this. And no, this is a partial differential equation which we get after solving all this. It's a partial differential equation in new particle velocity. Now we have to solve the PDE. We are using two theorems. One is using existence theorem that we have studied, I think, in the first semester, in which we are using a form like this, which we'll substitute here, and we'll get this expression, and we'll equate each coefficient of r to 0. And if we do that, we'll get n equal to 0, a1 equal to 0, and we'll get this expression, which is where this expression basically, which is valid for all j's greater than 1. And when if we get for even j's, we'll get this expression for all the odd j's, all the coefficients become 0. And if we directly substitute that, we'll get the u1 first solution, and this is the final solution. And a term which comes here, which is k, it's called perforation constant, which will be using in many times throughout the derivation, which is equal to r root of omega rho by mu. It's called perforation constant. Now this is the first solution, but this can be reduced into a not so complex manner by like this, because we know the Bessel function. This is the Bessel function of first kind of qth order divided by this. If we put q equal to 0, it becomes Bessel function of first order of 0th order, which I have done here. And by substituting x into k root of minus I, we'll get this expression, which is same as u1. So we can say the first equation is u1 equal to j naught k root of minus I. And there is another trivial equation which we get just by substituting, just by using all the partial differential equal to 0, we'll get the trivial solution like this. And this is the final solution, where a is the all the coefficients a0 a2 included, and this is the final u solution which we'll get. Now from here, uh, actually I have analyzed about 3 hole profiles, which is a cylindrical hole with concentric shells, and a general hole profile. And for all these profiles, till the last slide, the equations are same. So from here it changes. So we'll analyze it one by one. First, it's a cylindrical hole. Now for a cylindrical hole, we know this equation which we derived till the previous slide, and the boundary conditions are at r equal to r0, which is at the boundary u equals 0, which is basically the non-slip condition. And if you substitute that in that, we'll get the value for a, and if you substitute, this will be the value where care the perforation constant as this value. And we have to find the average velocity for the hole. This is basically for cylindrical holes. So you'll by using this equation 2 by r0 square, which we got by equating mass continuity equation, and we just by substituting, we'll get this enormous equation. And by using this identity, where we integrate 1/0th order Bessel function to get a first order Bessel function, by using this, we'll get the final average velocity equation like this. And I think I have said this is the pressure gradient, which we can substitute as delta P by thickness of. Now we know the acoustic impedance is basically pressure divided by velocity. So this is the equation. Now we know U bar equation. We know this equation. So we'll substitute U bar, and we know psi is equal to delta B by TH. So delta B get cancelled, and we get the whole equation for the whole. This is small, so it's basically specific acoustic impedance for the whole for in the case of cylindrical holes, as you can see. Now we can again reduce this equation by the conditions as given below. K, if k is less than 1, this Bessel function reduces to this expression. If the k is greater than 10, this reduces to this expression, which on substituting we use this. But for our case, it's between 1 and 10, and for this is the final equation for cylindrical holes. And now for cylindrical holes with shells, second problem. So suppose in the cylindrical holes there are shells, multiple shells. Suppose there are q number of shells in between. So if there are q number of shells, suppose this is the first shell, so this I'll consider as the first cavity. The second shell, this in between the shell, say second cavity. If there are q shells, there will be q plus 1 cavity. Suppose we'll name it as m equal to 1 to q plus 1. And suppose Rmi is the inner radius of the mth cavity, and Rmo is outer radius of the mth cavity. Same. So we know we derived this equation just before the different hole profiles are there. And this is the boundary condition. That is basically it's at all the boundary, at all the solid interfaces, the velocity becomes 0. First, for the inner cavity R1i, and for all the other cavities Rmi and Rmo becomes 0. And if we substitute, that is the boundary condition. And for each cavity, you have to take individual cavities. For each cavity, there will be an average velocity, average particle velocity, which can be taken from this equation. And for each cavity, we'll be getting a similar this specific acoustic impedance of cavity as this. And we'll be finding for each cavity. These are for this is for one hole, one hole, and these are for each cavities Z1 to Zm. And as you can see from our electroacoustic analogy, all the holes are actually in a parallel manner, and we can say the total impedance as the case of total resistance as like this hole, and that is the cylindrical hole acoustic impedance equation for a cylindrical hole with shells. Now the third case arises, which is general hole profile. Suppose the hole is of not cylindrical, just like an profile r of x, which is a function of x, but it's an axisymmetric case. And I think the same derivation applies, in which we take a small element, annular ring element, and we get the average velocity at depth x. X is given below, but the case here is in which perforation constant is a function of rx, which is a function of x. But in the previous cases, it was just a function of r, which is not a function of x. And in this case, for derivation, we had to use the volume velocity. Why? Because in this general profile case, as you can see, the area of cross section at each section is different, which is not the case in the cylindrical case, in which the area of cross section was same throughout the axial direction. So in this case, we had to bring in the volume velocity term, which has an area which is equal to I think we have said area into particular velocity, and which ax is basically pi rx square. Then we'll find the acoustic impedance term by substituting. Then we'll get for the entire hole. So this is for a part at an axial distance x. This is the equation for acoustic impedance. When you will integrate for the whole hole, we'll get like this. And this is for the specific acoustic impedance for the whole hole from 0 to th. Now, so in all the three profiles, I have derived specific acoustic impedance for the whole. Now we have to find the acoustic impedance of the for whole MPP. We know the acoustic impedance of the MPP is basically acoustic impedance of whole divided by number of holes. How this came, like if you look at this, in between the microperforated panels, the pressure, if you can if you look at this, basically a type of parallel connection in resistance. So, and also for each hole, the acoustic impedance is same. And if you calculate it, we'll get the total resultant resistance is equal to individual resistance divided by n. So it comes like this, and there is a number of holes, and we have to convert it into specific acoustic impedance, which is basically an area of cross section term. And if you all apply that, we'll get the acoustic impedance of MPP is whole divided by mu, but mu is a percent perforation, which is the ratio of sum of cross section area of all the holes divided by area of MPP surface. And this is the characteristic relative acoustic impedance, which we got by rho 0 r0. This is the relative acoustic impedance of air cavity, which is the capital D cavity. So we got the both of the we got the impedance of the MPP and the air cavity. By adding it, we got the total impedance. When using total impedance, we get the coefficient of sound absorption as given here. And now after this, I have programmed for the cylindrical case as given here. I have used the terms, and I have given these are the equations which I have used for total acoustic impedance and for the alpha absorption coefficient. And for verification, I've used from this paper. As you can see, acoustic properties of materials under the 3D microperforated panel I have used, and in which they used 4 microperforated panels, the difference being only the perforation ratio. So they are used, and I have used the same values for all of this, and I have plotted it. And this is my plot, and this is the plot from the paper. So you can see it's actually similar. And this is a program for the general profile. The previous one was a program for the cylindrical case, which we discussed at the first. This is program for the general profile, and in which I have used this function as a general profile. Why I use this? Because in a paper there was verification using this value, so I used this. This is a trapezoidal kind of profile, and this is used for various tapered values. Sorry, tapered, and in which the exposed side is 0.8 millimeter and the back side of the hole is 0.5 millimeter. It's a different profile, and I have used the values, and I have done verification, and this is what I got. And in this, the solid line denotes the tapered hole, in which this solid line denotes, and you can see it's actually the similar 0.7 and zero point 0.7. And now I'll get into inverse problem. So what inverse problem is? In the previous, it was a forward problem where we got absorption coefficient versus frequency data. So by using absorption coefficient versus frequency data, we will be reverse problem and get the acoustic properties and instant wave characteristics, these values. So how we are be using? I thought I used genetic algorithm. So what genetic algorithm is? Basically a method for solving both constrained and unconstrained optimization problems based on natural selection process that mimics biological evolution. So what it means is, it actually in each step from the general population, this genetic algorithm takes a part of a random selected population and makes them the parents of the next step, and or in a way you can say the next children. And that process goes on until it gets an optimized solution. That's the basis. And this genetic algorithm is used when the objective function is discontinuous, non differentiable, or highly non-linear. And in our case, it becomes highly non-linear, so you have to use the genetic algorithm case. And the steps used is, I defined all the equations, same as in the forward problem. Now I substituted numerical values on variables that need to be used, that need to be found using the algorithm, and I left the variables that is to be found in the symbolic nature. Then I defined an error function, or genetic algorithm nomenclature. It's called a fitness function, which is basically the sum of this is area, the sum of alpha from the graph minus alpha from the equation whole square. So I had to optimize this function using genetic algorithm, and this equation will be having the variables for which you have to find the values for. And for verification purpose, I used this paper in which they used a sample, and the values that I have marked. This is the things which I was planning to find. This is the thickness and the hole diameter. Hole diameter is 0.6 millimeter. It's 1.02 millimeters. And this is inverse problem that I did. As you can see, this is that I used here. These are the non-variables. This is the fitness function that I talked about. These are the fitness functions, and this is a fitness function in terms of an array variable to be used. That the previous fitness function has to be changed in a manner which can be used in the genetic algorithm. After that, I used the genetic algorithm as here, and I got the final results for which I got 5.94 in 10 power minus 4, which is 0.59 millimeters, same as 0.6 millimeter, and the thickness is 0.001, just 1 millimeter. Actually got the same, as you can see here. And this is the error function for this value. Thank you. That's all.